Hi. I hope I'm audible. If I'm not audible, please let me know in chat. Yes. I'm Pushpita Chanda, and I'm a PhD student at IIT Delhi. I'm a PMRF fellow, so that's why I'm the one of the tutor, or I guess I'm the only one tutor for this course, Applied Optics. Mm, Before joining PhD, uh, am I not visible? Oh, okay, sorry. Hi, I'm Pushpita Chanda. I'm a PhD student and the tutor of this course, Applied Optics. Before uh, joining this PhD, I was an MTech student at Applied Optics in IIT only. So, I'll try to follow the course structure professor has given, uh, and follow that path. So, basically, let us start the tutorial session here. Since none of you has commented that I'm not audible, so I assume that I'm audible. So, although the professor has already explained the basic things very well, uh, I want to quick make a quick recap before discussing new things and the questions. So, basically, optics or light or the phenomena of light. So that constitutes optics. So why well I'm saying phenomena of light, that means basically optical wavelength. So we know the optical wavelength is almost 4,000 to 7,000 angstrom, not angstrom, nanometer. Admit. But nowadays, modern optics, the people who work in modern optics, they work beyond in this range also. They work in terahertz, other works in IR, infrared, some work in UV light and all those things. That also constitute the optics part. So, but here we will like only focus in the optical wavelength basically. Sorry, here it is indeed angstrom. So this is basically 380 to 750 nanometer precisely. And that is called optical wavelength. So the phenomena of optics can be described by ray optics, wave optics, and nowadays we can also describe it by quantum optics. So in ray optics, as professor has already mentioned, that we assume that lambda is almost zero. And by ray optics, we cannot like describe some optical phenomena like diffraction, because in according to ray optics, diffraction doesn't occur. Some um, because the wavelength is almost zero. And in wave optics, we have finite optical wavelength. So basically, that is vary between 380 to 750 nanometer. And we assume that light is an electromagnetic wave. And in quantum optics, light is a part of light is constitutes of quanta. So this quantum optics domain is very modern, and this quantum optics, basically this is not part of this blood optics course, but let me tell you that the quantum optics is the basics of the quantum communication, and the quantum physics in general. The quantum computer, many of you have heard of it. The quantum computer is much faster than even super classical computers. So the quantum physics and quantum optics is the backbone of that quantum computer and quantum communication. So in this course, we mainly focus on ray optics and wave optics. So, so as you know, that the course has been divided in 12 modules, and each week we will go through each module. So first week we will discuss geometrical optics, basically, and in that we will discuss the Fermat principle, law of reflection and refraction, and so on. So we know that we can denote the wave as a function of position and time. So we are considering one dimensional wave. So that's why psi function is a function of xt. Otherwise, if we want to discuss 3D wave, or the wave which propagates in a dimension, it would be x, y, z, and t. So the 1D wave can be described as a function of x and t, more precisely function of x minus vt. So the v is basically the velocity, and more precisely we say phase velocity, the, the velocity with the which phase moves. So a propagating wave has some phase. So the phase move with the velocity, that is generally is a phase velocity. So this wave function psi can be written as a sine kx minus omega t. Or you can also write it sine kx minus omega t, whichever convention you want to follow. That actually doesn't affect very much, but when you follow a convention you need to stick to that. You cannot change the convention in between any calculation or number of calculations. That's the key thing. And you need to understand that when you are saying a sine k x omega t, so at x is equal to 0, t is equal to 0, uh, this is called phase. So the phase becomes 0. While at x is equal to 0 and t is equal to 0, the cos function doesn't become 0, it became 1. So you need to be very careful about these things and uh, understand that thoroughly, because whatever you understand, upon basis of that understanding you are going to solve the questions. So we have known that psi x t, or the wave, can be written as a sine kx minus omega t. So the k is called spatial frequency as well as wave vector, which is equal to 2 pi by lambda, and omega is basically 2 pi into frequency, or sometime we write as 2 pi mu, whichever is more convenient to you, that's totally fine. And mu, as I said, this is spatial frequency, and lambda we know wavelength. So what is a wavelength? So in simple words you can say that after one wavelength the wave repeat itself. The phase, when I say the wave repeat itself, is basically the phase will be the same. So from this to this is one wavelength. Similarly, from this red point and this red point will be one wavelength apart, and they have the same phase. So after each wavelength, the phase repeats. And similar to spatial frequency, there will be a temporal frequency and a counterpart of wavelength, which we call time period. Similar to wavelength, always remember when you are showing time period, so the x-axis would be t and this will be the magnitude, or you can write psi xt, and here x-axis will be the position and this would be psi xt. So after each time period, the phase also repeats itself. So time period is basically lambda of v, and time period can also be written as 1 by nu, this frequency. So from this equation we can also say that v is equal to lambda nu. So sometimes v and nu can be confusing, like my handwriting is so bad that sometimes v and nu can be confusing for you guys. So I will try to use f. So f and nu is the same thing. V is velocity, and so we can write angular frequency omega as 2 pi y 1 by tau. So later we will also know that when we write omega, we are like denoting only one frequency, or we call it monochromatic. But in general, yes. Okay. But in general, waves are not monochromatic. When a wave propagates, actually not one wave propagates, it actually a wave packet. What I was saying? Okay, yeah. So in general, in real life, there isn't any pure single frequency or monochromatic wave. The waves actually propagates as a packet of waves, that is called wave packet. So when you get to know the wave packet description or wave packet phenomena, you will know that there is called thing phase velocity. There is a thing called group velocity, which is uh, similar to phase velocity. But when we are discussing wave packets, we cannot say phase velocity. So that's the thing. Okay. So for now, we only stick to the definition of single frequency, and basically in single frequency we assume that bandwidth is almost zero. So the bandwidth means the frequency, and there should be, like, if a frequency, let's say 5 hertz, so it cannot be purely 5 hertz. It should have some bandwidth, like from 4.5 hertz to 5.5 hertz. So this is called bandwidth. So this bandwidth is almost equal to zero for a single frequency monochromatic waves. And this thing is called phase. Let's say this is a wave. If we follow sine function convention, both sine and cosine is a sinusoidal wave equation, and to describe a wave we always follow sinusoidal equation. Both sine and cos will work. So if we follow sine kx minus omega t, we know for the sine function at x is equal to 0, if this axis is x, sorry, this axis is not t, x, and this is psi. X is equal to 0, sine kx omega t becomes 0. When t is equal to 0, we know there is no initial phase. But if the wave is that, if we follow sine convention, there is an initial phase that is called epsilon. So this part kx minus omega t plus epsilon is called phase, and this epsilon is called initial phase. But if we consider cos convention, then we know that cos start at x is equal to 0, cos is 1, and so there is no initial phase. But here, if we follow a cos convention, there would be a initial phase. So that is what I meant, that you can follow either of the convention, but you need to be clear in like in the description and all those things. So if we take partial derivative at constant t, we get omega of the phase, and if we get it partial derivative of phase at constant x, we get k, and phase velocity is del x by del t. We can write it like this: t and del phi by del t. No, we need to take a mod, otherwise there we will get a minus omega x. We get omega by k. So that is called phase velocity, and from this we can also quickly remember a very basic formula, that is refractive index, which is n is equal to c by v. The c is the velocity of the light in vacuum and v is the velocity of the light in medium, basically. And we know that light waves follow the superposition principle. So if psi 1 and psi 2 obey the wave equation, and then psi 1 plus psi 2 also follow that. And we know the wave equation is this. This is second order differential equation. And we can write the wave equation as r e to the power I theta, and with basically real part of r. So instead of r we write a, and in place of theta we'll write that of phase. So we can write wave equation like this: e to the power theta is basically cos theta plus I cos theta plus I in sin theta. So real part of e to the power I theta is basically cos theta. This is the real part and this is the imaginary part. So this is basically a recap. So then we have seen the Fermat's principle. So another thing, if the wave, depending on the wave propagation, because there is a very small like MCQ kind of question, if wave is propagating positive x direction, then it is a sine kx minus omega t. Omega t minus kx. But if the wave is propagating in negative x direction, then it would be a sine omega t plus kx. Then the most important principle in the geometrical optics or ray optics is the Fermat's principle. So basically, Fermat didn't give a reflection law of reflection or law of refraction. He gave a simple formula or simple principle. From that principle, law of reflection and law of refraction can be derived. So, so what does that principle says? That principle says the ray will follow a path for which time taken will be extremum in comparison to nearby paths. So if a ray wants to go from A to B, it can follow different kind of path, actually infinite number of paths, but it will take that path for which the time will be extremum. Extremum means either it will be minimum or the maximum. So to prove that, we can, like, the detailed proof the professor has been discussed in the uh, lecture 3. So basically we divide the path in very fine infinitesimal paths, like say ds. So to cover the path, the time taken is d tau, so which is basically distance by velocity. Velocity is again c by n, so it became n ds c. So for ds path, it's time taken d tau. So for whole path, tau will be basically integration of n ds by c. We can write it as a summation also. C is constant, so sorry, C is constant, or we live in a realm where C is constant. And so this is the integration. So this quantity is called optical path length. So to be time extremum, that means maximum or minimum, the first derivative of it should be 0. So basically the first derivative of integration ds should be 0, and from this thing we can say the law of reflection, that sine theta 1 is equal to will be sine theta 2. Basically theta 1 is equal to theta 2 when the reflection is considered. That means angle of reflection and angle of incidence will be equal, and the incident ray, reflected ray, and the normal at the surface will lie on the same path. So that has been shown in the class. And also law of this is law of reflection and law of refraction has also been established, that is n sine n1. So in reflection, the ray, the reflected ray, is in the same medium as of the incident ray. But in refraction, what happens, that light basically falls on the surface and it goes away from the normal, or it comes near to the normal in the another medium. So if that is angle of incidence and that is angle of refraction, and this medium is n1 and this is n2, this is sine theta 1 is equal to n2, n1 sine theta 1 is equal to n2 sine theta 2. And for refraction also, the incident ray, the refracted ray, and normal to the interface also must lie in the same plane. So there we can consider when I was discussing optical wavelength, I wanted to give an uh, okay, some example, that not like question 1, but still for the sake of numbering we can say that a straight hollow pipe of 1 meter long is closed at both ends with glass plates of 1 centimeter thick. If the pipe is evacuated So my call can be disrupted because there is a time limit apparently. So if the call get cut, please join with the same link. Queued. Then what would be the optical wavelength between the glass surface? So the optical, optical not wavelength, path length. So we need to multiply with the distance with the refractive index. So the refractive index of the glass is basically 1.5 into 1 centimeter, so that is 0.01 meter plus, so this is how the cylinder is. So this is the glass, then 1 meter of evacuated, that means vacuum, plus again 1.5 into 0.01 in meter, this is 0.01 meter. So in total that would be 1.03 meter. And if the pipe is filled with liquid whose refractive index is 1.33, then optical path would be be 1.5 into 0.01 into 2, because there is two surfaces, and 1.33 into 1. In total it would have been 1.36 meter. So we can see what is the optical path wavelength. Now we focus on the ray equation. So in nature we have seen that there are some time when we get to see that the light get refracted from N1 to N2, then from N2 to N3, from N3 to N4. Because of this reason, we see some star blinking. Not some stars get blinking. Planets are more, the light from planets come from very less distance, so that is stable, far more stable than the light from the stars, and the stars blinks. So basically light follows multiple refraction, and for this reason also people see mirages in the desert. So when this occurs, so this is angle of incidence, this is first angle of refraction, this is also be phi 2, and this will be phi 3. Similarly, this will be phi 3 and this will be phi 4. But this angle is theta. So this is theta 1. Similarly, this is is theta 2. This and this is theta 3 and all those things. So we this is Snell's law or angle of refraction and so on. So from n sine, sorry, I shouldn't write it like theta for that case because we are denoting the angle phi 1 phi 2. So n1 sine phi 1 is equal to n2 sine phi 2 and so on. Ni is equal to sine, sorry, not ni into sine phi I. So sine phi would be is equal to cos theta. And we can say that n is a function of x because in this direction we are assuming that x cos theta x, that theta is also a function of x because here theta 1 changes from theta 2 and it is also different from theta 3. So with x the theta is also changes, is beta, which is a ray invariant. And from that we get to the ray equation, and how we get to the ray equation professor has explained in the lecture 3. That is dx by dz whole square is equal to n square x beta minus 1, or we can write a differential form, which is d2x dz2 is equal to 1 by 2 beta square dn square dx. Either of this is a ray equation. So remember, this is ray equation. And this is wave equation. Both equation can satisfy or describe a ray of light, or light, I should say light, but they are not same. They are different. This describe all the waves, and this is ray. It is ray equation, and from that ray equation you will also know that for homogeneous medium n doesn't vary with x, so this becomes 0, and when you like solve a second order differential equation, which is z to basically 0, the solution is a straight line mx. Yes, sorry, I should not say x. So mz, sorry, mz plus c. So from this, so ray equation depends on the farmers, basically depends on the Snell's law, and Snell's law came from the farmer's principle. And from this ray equation we get to see that in a homogeneous medium they will follow the straight line. And we also know that the shortest path between 2 points is basically a straight line. And the farmer's principle, hello, okay, so farmer's principle does say that they will follow the path which will take extremum time. So we also have seen that time basically means optical path length. So it's not like time is equal to optical path length, it's basically time is equal to optical path length by velocity of light in the vacuum, or we can say in the air basically. So here from that farmer's principle we get the Snell's law, and from the Snell's uh, law we get this ray equation, and from this air equation we get, if the light is traveling in a homogeneous medium, it will take a straight line, and the straight line we know is the shortest distance between 2 points. So basically to cover a short distance, time should be also the minimum. So that is how we know that it all justifies the principle. We can say it comes from that same principle. Then we have discussed the formation of images, and from that we can say so basically this and this are the same image. Refraction, and these surfaces are the spherical surface, so this called convex surface, and this denote concave surface. Okay, so from these surfaces we get the Gaussian formula for single refracting surface, which is the called drops. So I have I've been enjoying the last meeting link. So I have created a new meeting link, and from now on I'll post the second meeting link in between the class. So let us resume what I was discussing. Uh, So on that, we get the Gaussian formula for single reflecting in surface, which is n2 by v minus n1 by u is equal to n2 minus n1 by r. So here n2 is this refractive index of this medium, n1 is the refractive index of first medium, and this is the r. So basically r is radius of curvature, and u is object distance, and v is the image distance. And v is the image distance. And remember here the sign convention has already taken care of. So put the u. You don't need to put the minus sign here. So put directly the u and you will be okay. So if we start with this concave surface also, you will get the same like get the same result. Let me show you. So we know that Newton's law says that N1 sine I is equal to N2 sine R. So if we divide sin I by sin alpha by N2 sin R by sin alpha, so this is I and this is R and this is the alpha. That can be written by this is sin I, so that can be written by CO and sin alpha that can be written by AO. Similarly for this to be CI and that will be AI. So AO can be written as PO and AI written as PI. So N1 CO can be written as O PO minus CP and can be written as PI minus CP and PO and PI. So this U is equal to minus OP C is equal to minus R and E is equal to minus PI. So if you put this value we will get 2 by v minus n1 by u is equal to n2 minus n1 by r. This is the value. And from the reflection, reflection by single spherical surface, we get the equation 1 by u plus 1 by v is equal to 2 by r. And from a lens, thin lens, we get to the formula of this 1 by f is equal to n by minus 1, 1 by r1 minus 1 by r2. So f is the focal length, and depending on these values we can say that if f is negative, that is diverging length, and f is positive, converging. So that also depends on 1 by r1 minus 1 by r2, and also this n minus 1. Here n basically when n1 by n2, so basically the medium of the length is n2, and here n1 and n1. Then also the case if that n1 is greater than n2, then also the converging, even if the lens is converging, it will act as a diverging lens. And how the image is created, that you have known. So the lateral magnification can be written as f2 plus x2 by f1 plus x1. It can be written as minus f1 x2 or minus x2 f2. Another thing is the lenses this is called bioconvex lens. So for bioconvex lens, if this is R1 and this is R2, from the lens middle point, this is in the left, so R1 is less than 0. Okay, so if this is, I made a slight mistake. Let me, oh, this is R1 and this is R2. So this is R1. So from middle of the, even though this distance is from that to that, for thinness this distance is very minimal. So from the lens, middle point R1 is at the right, so R1 is greater than 1 and R2 is the left, so R2 is less than 0. So this is diagonal, this is convex lens, this is concave lens, where R1 is less than 0, R2 is greater than 0, because this is R1 and this is R2. This is called bioconvex lens because both are the same. And there is the case here where both are negative, and there is the lens case where both are positive. And this is plano convex. And if this is R1, here R2 is negative, R1 is infinite. So when someone says the radius of curvature of a convex lens, you always need to know that they are talking about R2, because for the plane side the radius of curvature is already infinite. So the magnification and all those things, regarding this there are more formulas. One of this is Lagrange's law. Lagrange's law. I don't want to derive that law, but I want to say that, and what is object size. And then y2 is the image size, and you see this is alpha 1 and this is alpha 2. So if you place a object in front of concave spherical surface, you will get the image at here, and how the image is formed, that has been discussed in the class. So, and what is alpha 1, alpha 2? So this is the equation, the with this in addition to Snell's law, when image is formed, this will also be followed. And there is another thing called Abbe's sign condition. Condition that is kind of extension of this thing, which is n1 y1 sin alpha 1 is equal to n2 y2 sin alpha 2. And the generalized form of this equation is basically n minus 1 y n minus 1 when there are multiple image formation is equal to n y n tan alpha n. So this is Lagrange's law, and this is Abbe's sign condition. Now let me discuss some question. First, some question similar to the question asked in some question are basically theoretical question. I have discussed the theory for so long to just because you can understand this question better. And now some question, that is one question is a light ray passes from air into light ray passes from air into water at an incidence angle of 45 degrees. Find the angle of refraction if the incident ray has a wavelength of 600 nanometer in the air, what is its wavelength in water? So the answer is, we know N1 sine theta 1 is equal to N2 sine theta 2. So theta 1 is 45 degree, N1 is air, so 1, N2 is water, so 1.33. So basically that would be 1 into sine 45 degree is equal to 1.33 sine theta 2. So sine theta 2 would be 0.7071, 1.33, which is 0.532. So theta 2 is sine inverse 0.532, which is equal to 32.2 degree. This is the answer. And for the second part now, the wavelength of the medium is lambda medium equal to lambda AYM, which is 600 by 0.33, which is 451 nanometer. Then a type of question is, a wave has the form psi xt equal to a sine 2 pi t minus kx. So if the phase velocity is 4 into 10 to the power 8 meter per second and k is 2 into 10 to the power 6 meter inverse, find the angular frequency. So the answer is, what is omega? So we know P is equal to omega by K. So omega is equal to V into K. So it should be omega, it should be in second inverse. So basically that follow the dimension also. It is 4 into 10 to the power 8 into 2 into 10 to the power 6 rad per second. So that would be 8 into 10 to the power 14 rad per second. They are very simple. We need to know this formula. K is equal to 2 pi by lambda, omega is equal to 2 pi mu, and 2 pi by tau, omega by K is equal to V. Those things. Another thing was the question 4, which is an object and its image are positioned at 10 centimeter and 20 centimeter respectively. From the respective focal points of a lens. What is the focal length? So we know the Newton's lens formula. X1 x2 is equal to x square. So here origin is 2 x2 x square. So here x1 is 10 centimeter, x2 is 20 centimeter, and f square would be 10 into 20, 200. So f is equal to 200 equal to 14 into 14 centimeter. So according to Newton's length formula, the x1 into x2 must be constant. Now some another thing you all know, that is the power of a length equal to 1 by f. This is power of length, and its unit is diopter. Of the So question 5. Is a small air bubble in a sphere of glass 3 centimeter in diameter appears to be 1 centimeter from the surface when looked along a diameter. Find the true position of the bubble given the refractive index of glass is 1.5. So our air bubble is in a sphere of glass. The glass sphere is 3 centimeter. And the air bubble appears to be 1 centimeter from the surface when we look along the diameter. So we have our actual image, and this is a concave surface. Because we are outside, so m2 by v minus n1 by u is equal to m2 minus n1 by r. So v here we need to take minus, because in convention we generally give v plus, so that is minus 1. R is equal to minus 1.5. n1 is equal to 1.5. So in the convention, u is taken as minus. So if u is in minus, then it is minus. So if you put all these things, then u is equal to minus 1.12 centimeter. In all this value will fit air is equal to minus 1.12 centimeter. And the last question is a concave lens of glass n is equal to 1.5 as radii of curvature 15 centimeter and 30 centimeter. Find its focal length in air. What will be its focal length in water of refractive index 4/3. So a concave lens of glass has radius of curvature is 15 centimeter and 30 centimeter. So what will be the focal length of the water of with its focal length in water of 0.3? So we need to first calculate. This is second time we need to do this. First we need to calculate the F1 by F air, which will be 1.5 minus 1 by R1 minus 1 by R2. So the concave lens, so this is glass, and this is air here and air here. So focal length in air, we calculate that. So 1.5 minus 1, which is known by minus 15 minus 1 by 30. So that would be F air is equal to minus 20 centimeter. And now we need to calculate in water, and that is, we know N1 minus N2. This is N2, this is N1, this is N1. So N1 okay, this is actually N is equal to N2 by N1 for writing those things. Sorry. N2 by N1. So N2, which is the medium of the lens, that is still glass, so 1.5 by 1.33 minus 1 and then minus 1 by 15 minus 1 by 30, and if I put this thing, that would be minus 80 centimeter. So these are kind of the question. If you understand this question, you can easily solve the quiz. So that's for today. More in the next class. Thank you.